Okay, so I would like to welcome everybody and mostly welcome Renato Renner, who is my PhD advisor who will give the colloquium today. So Renato studied physics at EPFL first and then at ETH Zurich. And after studying physics, he decided probably that he wanted to be an interdisciplinary researcher maybe and joined the computer science department to do the PhD on the Uli Maurer, who is a cryptologist, cryptographer in classical cryptographer. And during this PhD, he defined a proper way of how we should think of security in quantum key distribution, and was also able to show that protocols like BB84 would satisfy these definitions. So that was that. Then he went to Cambridge, University of Cambridge, to do as an HP research fellow. And since 2007, he's at ETH Zurich. Since 2015, as a full professor in theoretical physics. Now, he received some awards on both for his teaching and for his research. But maybe more interesting is what he's known for. So he's known for his work on cryptography, quantum cryptography, and many of the techniques that he developed in quantum cryptography have been used in other areas of quantum information theory, like resource theory or Shannon theory. And the second thing he's very known for is his work on the foundations of quantum mechanics, which today's talk is related to. And there, I would say that the big contribution is to make problems that philosophers would maybe discuss back and forth for many years, to formalize them in a mathematical language so that they can actually be answered precisely and definitely. So I'm really looking forward to today's talk on the accuracy of clocks.
Okay, thank you very much, Marco, for the introduction. That's very nice. I will indeed try to follow that spirit and make some concept which is at the foundations into something which is more mathematical, accessible. So first, I would also like to thank the audience for being here. I see many familiar faces, or I should say names at least, on the screen. So that's of course a pleasure to see them. It would be even more a pleasure to meet these people all in person, and I hope this will soon again be possible. So as was already mentioned, please feel free to ask questions during the talk. I'll be happy to answer them immediately. But let me start. I would like to start with a hypothetical conversation about one word that appeared in the title, namely clocks. And of course, one could ask me, what is actually a clock? And my answer, and this is really from information theory, which is mostly operational, would be in that direction, a device that measures time. But then, of course, the obvious follow-up question is, what then is time? And to be honest, I don't have an answer to this question. So I'll just give a citation of someone else. And I think it's the oldest citation that will appear in this talk. It's, I think, yeah, almost more than 1,800 years ago. But the answer was already there, clear that it's not an easy notion. So Augustine of Hippo, he's I think the first person who really thought, or is known today to be one of the first who thought very deeply about the notion of time. Maybe less about clocks, but certainly about time. And I think many of the ideas that he mentioned already in his in his work that is mentioned here are still very relevant today. For example, about the subjective notion of time and so on. But his short answer would have been, if no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know. And I think we all have, of course, a perception of what time is, but it's really hard to formalize. I think this is nicely expressed by this sentence. Of course, we are now much more advanced in our, let's say, I should say, description of nature at least. hopefully also a bit in the understanding of nature, but at least we have descriptions of nature which are extremely accurate, for example, quantum theory. And they tell us at least something about time. But in modern physics, we have to be aware that there is not one notion of time. There's a notion of time in quantum mechanics, for example, and one may even debate within quantum mechanics what the proper notion of time is, because if I now cite here as an example the Schrödinger equation, a quantum field theorist could come and say, no, I don't want to use the Schrödinger equation, I use something else, and so on. But so this should just be understood, this slide should be understood as showing that there's still a variety of notions of time today in physics. And of course, one very familiar notion is the one I've shown here. It's the time that appears as a parameter in the Schrödinger equation. And of course, it's well known. This was pointed out by, I would have had him as a colleague if he lived longer, Wolfgang Pauli, is also from ETH Zurich, who made this claim, which he also proved, that there is no quantum operator or no observable that could measure time. So time is not an observable like other things that we usually consider observables. For example, the position of a particle in quantum mechanics. But there are also other notions of time. And one appears very prominently in general relativity, where time is essentially a parameter which tells us how far we have moved on the world line. And this parameter is different for every world line, meaning that it's really already, it has a subjective notion, or it is a subjective notion. And then there is also time appearing in thermodynamics, and this is maybe the only theory where time appears fundamentally asymmetrically. It tells us that heat will always flow from a hot reservoir to a cold one, never the other way. That's the second law, essentially. And of course, also here one could debate whether this is always true. There may be statistical exceptions, but my point here is that thermodynamics is not giving us a time as a quantitative measure, but a time direction. So we have all these notions in physics, all these answers, so to speak, in physics about the question, on the question, what is time? And clearly this answer is not conclusive. Now we could also ask the question from a different angle and just ask ourselves, how do we define time? Or what's, for example, the definition of a second? And the second was defined for a long time just by the subdivision of the length of a day. And of course, the length of a day is defined by the rotation of our planet. So that we could also see that as showing that the rotation of a planet serves as an extremely accurate clock, one that was considered so accurate that we should take it as a definition of the second. Now, the modern definition is kind of almost the opposite of the old one. It's a very small object that defines time, namely an individual cesium atom. And modern atomic clocks measure time, or at least some of them measure time directly according to that definition. So they look at essentially the energy level difference between two states of this atom. Now, obviously, if you want to relate it to the previous slide I've shown, the left-hand definition is one that relates more to this classical notion of time, which is still, let's say, similar to the general relativistic one. And that's the notion is in some way, the notion of Einstein in general relativity is a natural generalization of the notion of time in mechanics, in classical mechanics, that we would use to describe the rotation of the Earth. And then, of course, on the right-hand side, the modern definition refers to quantum theory. Obviously, you couldn't describe it with GR or classical mechanics. But one has to be aware of the fact that also the thermodynamic notion of time enters implicitly, because when we define time via classical theories, we would still not have a time direction. So if you, for example, talk about the rotation of the planet and would give that definition to an alien who has never seen our universe or our Earth at least, then he wouldn't know in which direction it rotates. So he would still be missing the time direction. So he has the definition up to this bit, and the same is somehow true for this quantum mechanical definition on the right-hand side. So we also have implicitly this thermodynamic notion that provides us with a direction. Okay, so these were very general statements. Now I want to be a bit more concrete. And as Marco pointed out, I was always interested in information theory, and in particular in the information-theoretic view on other things in physics, for example, time. And one could therefore ask the question, what information does a clock provide to us? And again, this is kind of an operational question, because if you ask about information, we have to ask information about what. And of course, if I now say information about time, then I'm back at this problem of having to define what time is. But we could ask ourselves, what do we actually use clocks for? And if you think about this, then obviously one of the uses, for example, was that I observed my clock to know when I have to log into this talk and start this talk. And probably you did the same, to know when you have to start listening and log in. So a clock establishes correlations in time. And of course, if there was only one single clock in the universe, and of course I'm counting everything that could be used as a clock, like any natural phenomenon, that like the rotation of the Earth, that could be used as a clock, also as a clock. So if there was only one, it would be completely useless, I would say, because it's not correlated to anything else. So what makes a clock useful is really the correlation between all the clocks we have. And of course, that's only one use. I'm not trying to claim that this is the only way we use clocks, but that can help us, this way of thinking can help us defining accuracy of a clock. So what are actually the questions that I would like to treat in this talk, in the, let's say, more detailed part of this talk? So far, this was a very general introduction. I would like to ask the question, what actually makes an accurate clock? And if you remember again, the first few slides, then there were indeed very different systems used as accurate clocks in the past, namely the rotation of the Earth, which is extremely big, I would say, at least compared to the system of a single atom that I need to define or to measure time with modern atomic clocks. And so the question that really interests me as a physicist is whether physics imposes any constraints, any fundamental constraints on the accuracy of clocks. And I've just, to illustrate that, put here this uncertainty relation on the bottom that is sometimes discussed. I put here a question mark. And there is indeed an interesting debate that has been going on over decades, whether such an uncertainty relation is true, whether we could say that there is a minimum accuracy or a maximum accuracy to which we can determine time, that would be the delta t. And then the claim is if you have a maximum energy available, then there is a fundamental bound. But there have been counterexamples to that and so on. And I think the bottom line for me so far of this discussion is really that this is just a formula. And to ask whether it's true or not depends on what you exactly mean by this delta E and delta T. But the debate is certainly interesting and actually quite instructive. But I don't want to further go into that because I want to go back to this operational approach, where we first ask the question, what are the relevant quantities that we want to consider, and only then ask the question, what could be relations about them. As a disclaimer for the remaining part of the talk, and because I realized in previous talks, I really made some experimentalists a bit furious, I should really say that I'm a theorist in the sense that I'm not going to care during this talk about experimental imperfections. What I mean by that is that I'm making statements about the theoretical scheme, and then whether these theoretical statements apply to real world situation, of course, depends on how close this real world experiment comes to that. And okay, one could say that this is an empty statement. Therefore, I want to give an analogy. It's maybe the same that we do in quantum computing. In quantum computing, as a theorist, let's say as a pure theorist, I would just talk about quantum circuits. And I can now reason about them, develop algorithms, do all interesting stuff. Of course, knowing that in reality, the real quantum computers or the real devices are not that perfect. And so, of course, both things are extremely relevant. We need this abstract level, abstracting away from the real world imperfections in order to make sure we just can focus on the relevant concepts on that level. And of course, we also need to understand the experimental imperfections at the end when we want to build a device. So I don't want to value the two. I just want to point out that I'm focusing now on the theory part. Okay. Now, the usual question that comes about is that if you now assume that everything is perfect, then we trivially have a perfect clock already given by, for example, a qubit system. So maybe you know from your physics classes that if you have a two-level system with a certain energy difference and put it into a superposition state between 0 and 1, then, this is now the Bloch sphere picture, so that orange thing would be the superposition state, and that state would start to rotate with frequency omega given related to this energy difference. And of course, if I now assume as I'm a theorist that everything is perfect, this clock would really move perfectly according to this equation. It would actually be the Schrödinger equation around with this frequency. So it seems that I already have a perfect clock and I'm essentially done. I don't have anything to do now. It would also, by the way, in some way violate this other thing because it's just a perfect clock. It moves perfectly around. Of course, that's not the full picture, as you may immediately see, because that's the clock. But at the end, I want to read off the time. So the right-hand side should be understood not as a picture of the clock, but just of the picture of a display of a clock. And so in order to have this display, I somehow need to interact with the left-hand side of the clockwork. But what I told you so far, the way this clock moves, the rotation of this state with frequency omega is only true if I put this box into or if I put this clock into a perfectly isolated box. So it has to be a closed system. Otherwise, the conclusion from the previous slide that it rotates perfectly is simply not true. So I have to remove the box again in order to actually read off time. And then, as you know from quantum mechanics, if I read off time, any reading of a quantum mechanical system obviously causes a disturbance of the system. So I will disturb the state of the clock. And therefore, again, my reading of the time will become inaccurate. I mean, that's all, of course, extremely well known. So far, I was not attempting to tell you anything new. By the way, I will not tell you much new except maybe for the last 3 slides, but I need all that to somehow introduce what's new. And okay, so that's well known. But we definitely have to go to larger clocks. So it's clear that if I measure a qubit, even if I try to measure it weakly, I will very quickly have destroyed its state almost completely. So it just seems hopeless to, with 1 qubit, extract enough information to really accurately measure time. You could also say it's as an information theorist, when I say it's all about correlation and about having information. It's clear that the amount of information I can have about the qubit is at most actually 2, not 1. I mean, at least to the information theorists, that should be clear that it can be 2. But of course, with 2 bits of information, I will not be able to feed a display which has much more bits. I mean, that's a very rough argument, but it turns out if you try to make these things precise, that this is actually a correct statement, because that's really like the interface, the left-hand system to time, to nature, and you just get 2 qubit or 2 bits from it, 1 qubit, but 2 bits of information, and that's just not sufficient. So this already tells us we have to look at larger systems. And of course, in real atomic clocks, there is not 1 single atom. There are many atoms. This could also be considered a larger system. So we need a larger system. So this orange clock should just stand for a larger clock. It's no longer a 1 qubit system or a 2-level system. And now we can, of course, hope that we can indeed, for a large enough clock, measure time. And that's what we do constantly when we look at our clocks. But still, of course, in reality, this clock is a quantum mechanical system. So I draw for simplicity now just 1 hand of the clock. And you could imagine, just as a picture, that the position of the hand of the clock is described by a wave function which has a certain spread. So the time is not perfectly defined in that sense. And this has some consequences, which are also quite obvious when you're familiar with quantum mechanics. Of course, the pointer of the clock or the hand of the clock moves, and this movement will result in a slight broadening generally of the wave function. But what is actually more important is that as soon as you measure the clock, so let's suppose I really want to know the time very precisely. So I measure the position of the hand of the clock to very good precision. Then you know from quantum mechanics that this will essentially be a measurement with respect to almost the delta function, or exactly as a theorist, I could even say. And then, of course, the wave function of the clock after the measurement would be essentially a delta function. Now, then I have really extracted, let's say, the maximum information. But the problem is that once I have a delta function, the further time evolution of the clock will be just the spreading of the system. So you could imagine the diagram is like that. The clock starts, the hand is in a certain position and moves nicely. Then I measure the time, I look at my clock. But then once I've observed my clock, the further time evolution of the clock is just a spreading of the wave function. So the hand of the clock no longer moves in a well-defined direction. And of course, if I didn't observe the clock, if I didn't do the measurement, the wave function of the hand of the clock would just have moved continuously, maybe still with a slight spreading, but it would have moved still into one direction as it should. So the bottom line of this is never look at your clock too precisely, because it will just destroy it. And that's, of course, just a picture of it, but that's indeed what's happening according to quantum theory. And this imposes limitations. So suppose we now want to use the clock as a stopwatch. So you have some race, someone starts, so I take the starting time, I look at the clock at the time when the start happens, and I look at my clock at the time of the finishing event. And now I have a choice. One variant would be that I look at the time at the beginning of the race not so precisely, so that the clock is not disturbed too much, and then it will evolve nicely until the end, and I can measure it again, and still at the end of the race, the wave function will be nicely peaked and gives me good information about time. Another variant would be that I do a very precise measurement of the starting time, so I really watch my clock with a delta function, but then the wave function just spreads a lot, and when I look at the clock again at the final time, I will just see an essentially random time. So there's a trade-off. The more precisely I measure the starting time, the less precisely I can measure the finishing time, and in some way vice versa. Of course, if I don't measure at the start, I have still a very nice wave packet at the end, but I didn't know when we started. Okay, so what do we learn from this? Again, I think I summarized it already. We have to find a trade-off. So that's here stated by this sentence, and we can ask ourselves, is there a quantitative result we can get from such considerations? Now, the consideration I've shown you is just for illustration. I will not argue in that way with stopwatches. In fact, I will generally not look at stopwatches any longer, but something more general, in the sense I will explain in a minute. So a stopwatch is essentially something which I could operate with a trigger. So I don't ask the clock to tell me time constantly. I ask the clock at one point in time what the time is, and at the end point. So I give the clock triggers, and then it tells me time. So that's what I will in the future, or in the following in the talk, call a stopwatch. But we also have our alarm clocks, for example, that wake us up in the morning. And of course, we don't constantly ask the alarm clock, what's the time? We are just sleeping. And then the clock autonomously tells us, now it's morning, you have to get up. Or more generally speaking, I call this a ticking clock. A clock sends out time signals autonomously. I don't ask the clock to tick, it still ticks every second. So there is really a fundamental difference between the two, in the sense that the right-hand side, the ticking clock, has to be an autonomous system which produces information without an external trigger. So it cannot rely on someone asking it and only then it measures time. It somehow has to continuously be aware of the time and emit this information. Whereas the stopwatch is in some way a simpler object. It doesn't have to produce anything unless it gets this trigger and then knows what to do. Of course, if I had a good stopwatch, I could still build a ticking clock, in the sense that I could just observe the stopwatch at random times and somehow put it together. It would be a bit difficult to do that, or I would need many of these or have to restart the stopwatch many times. But the point is, I will at the end, or I will in this talk, show you bounds. And therefore, if there's a way to use a stopwatch to build a ticking clock, and if I give you bounds on the accuracy of ticking clocks, they will also apply to stopwatches. But in the following, I will only talk about ticking clocks. In other words, I will talk about clocks which generate time information autonomously. Let me just briefly go back to how famous physicists, in particular Einstein, talk or thought about clocks. And I should point out that actually one could say the development of relativity theory was really in some way enabled, of course, by many things, but among others, also by the view on time, which was an operational view. So I think one of the main ideas is that if one wants to get a new notion of time, if you just start with classical mechanics and now think what could be a more general theory, then you shouldn't, of course, take the notion of time from classical mechanics. You have to do something more clever. And what Einstein did is he was thinking operationally about clocks in this way that is illustrated here as some light signal bouncing forth and back between mirrors, and you're just counting how many times it bounced back, and this gives you the time. So this just illustrates that an operational viewpoint is not something new in physics. This was actually famously used, of course, to develop one of our best theories we have today, general relativity, or also special relativity. Now, I will, in the following, just focus on quantum theory. And so in quantum theory, we can now also ask ourselves, what is a clock operationally? So it has to be a device which consists of somehow the clock itself that moves, that undergoes some evolution, and at the end, some way to extract information from the clock, to measure it. But as I said, the measurement is kind of not an active measurement from the outside, but it's an active action from the clock itself that sends out signals. And this right-hand picture should just indicate, as before, the display. This is not by itself a clock. This is just what it shows. Now, one general model, what could take, and I'm just saying that for those who are now more interested in the technical aspects, you could say that a clock, the evolution of the clock, because it has to send information to the outside, has now to be described as the evolution of an open quantum system. It's no longer a closed one. That was the point I was making at the beginning. And in order to describe the evolution of open quantum systems, we have to make certain assumptions. And one of the typical assumptions that one makes is a Markovian assumption. A Markovian assumption essentially means that if the clock interacts with the outside and sends, or that's so that some information that was inside of the clock is now in the outside world, in the environment of the clock, then this information will never return to the clock. So that's just this Markovian assumption. This is an assumption, but this assumption is somehow well justified if you think of clocks that tick, because of course the tick is just something that is sent away and the clock doesn't hear it again and cannot use it in the future some way. So that's the assumption we are making. But the picture of this assumption is really that if you have a clock, so these are kind of the ticks, these ticks move away and are never seen by the clock again. So you've seen it, so they just go through the clock, so that the clock always has a new piece of the environment that's entering here from the bottom, and then interacts with this piece of environment, and then it goes away. That's essentially what people call the Markovian assumption, or a picture of that. But technically, it's just a Markovian assumption that we are making here. But once you have made this assumption, you can discretize the time evolution. That's just, as a quantum information theory, is useful. And then in each infinitesimal time step, you can think of the evolution of the clock as a completely positive map that goes from the clock to the clock itself. So the clock moves, but it also outputs something to the outside. That's the T. So that's this map described here. And just as, on the level of what does it map to what. So it takes a state of the clock, generates a new state of the clock, and also emits something to the outside. Of course, there's also an input, but the input, as I said, is assumed to be uncorrelated to everything that happened before. Therefore, it hasn't to be given as input to the map formally. Okay, now one important question is, of course, how do we now measure the accuracy of a clock? Now I come back to this operational idea. And the operational idea, if you remember, was that if we ask the question, how much information does a clock give us about time, or how accurately does a clock describe time, then we are somehow left with the question, what is time? And I want to have something which is as general as possible. I want to have a definition which is ultimately even independent of quantum mechanics, because that's, of course, what we want. If we want to reason about time, we also have the goal of having an understanding of time at the end that goes maybe beyond quantum mechanics, and possibly, I mean, this all is of course somewhat motivated by the search for a theory which is unifying gravity and quantum mechanics. So we want to, as far as possible, get rid of constraints coming from quantum mechanics. So the definition of the accuracy of a clock should be independent of quantum mechanics. And here, this is one way we usually did it in the past, at least in my group. We looked at what we call the alternate tick scale. So that's something very simple, and I'm sure I'm not the first one considering that. You just imagine that you have two people with clocks, with, let's say, identically designed clocks, and you are interested in quantifying the accuracy of this clock design. They're just two copies of the clock. Now, as I said before, we are modeling clocks as devices that emit time signals, and the most basic time signal you can imagine is just a tick. I called it tick. It's just essentially a stream of zeros, and sometimes there's a tick which I would represent as a 1. So a bit again, in terms of a picture, you could imagine that both. So that would be the left thing, what is called TA, is the stream of outputs of the left clock. Again, I use this discretized notion, and of course the discretization shouldn't be relevant, but it's just here for the picture. And on the right-hand side, you see the output of the right clock, and a 1 kind of corresponds to the tick and the 0 to no tick. And now, of course, if you imagine having two clocks which are very accurate, then it should be possible to set up them in such a way that the ticks are always alternating. So first the left clock ticks, then you hear the tick from the right, again from the left, again from the right, and so on. And of course, if there were perfect clocks, this would continue forever. But now you could say, of course, if a clock is not perfectly accurate, at some point you're expecting this to fail. Of course, that will be a kind of probabilistic statement. This failure point could be at different times, but you could ask yourself, what's the average number of ticks that the clocks can emit until they fail to have this alternating order? So in this picture, you see first the left ticks, then the right, then the left, then the right, but here suddenly the left ticked twice before the right ticked. So here the failure would have happened. Now note, the important thing about this way of thinking is that this is completely independent of time, of an external time. We are just comparing two clocks, and it's a dimensionless quantity. I'm just counting the number of elementary time signals that the clocks emitted until they failed to be perfectly synchronized. And this is in contrast to other measures of time. And you say, what's the deviation in terms of seconds of a clock after such and such time? So this is really only, or maybe to illustrate it, if both clocks someone would speed them up by a factor of 2. You wouldn't notice that in this accuracy measure, because it just counts the number of ticks until they fail. So this definition is in some way independent of a background time. It just measures the accuracy of the clock with respect to itself, if you want.
Can I have a question?
Yes, sure.
So one thing I'm unsure about here is, it seems like we kind of need a background time to even define the discretization, or not?
Yes, that's right. Yes, I mean, that's a good point. Indeed, I mean, if I draw this discretization picture, I would need a background time. So what we actually do, I mean, okay, maybe I should first say, I started now with quantum mechanics and discretized it in order to have this completely positive map description. This is not necessary. I could just stay with a kind of open quantum systems equation, some Liouvillean and so on, and describe it in these terms, and then just say it's kind of a continuous signal with sometimes some peaks. So this is somehow a matter of description to some extent, but once I choose to describe it in that way, I have to show a consistency requirement, and the consistency requirement is exactly that if I change the discretization size, then asymptotically for small discretization sizes, this accuracy doesn't change. And there are some criteria which are pretty, let's say, in some way, I would say, once you see how they are stated, they look like very natural, which are exactly expressing that. So if we discretize, we bring in, so the short, maybe the summary of my answer, if we discretize, you're right that we bring in an external time. So we have to again get rid of it by putting in addition a criterion, consistency criterion that says actually brought it in as a technical means, but it's not relevant. If it shows a different one, it wouldn't change. That's a very good point. And that's what it was indeed. That's maybe why I shouldn't draw these discretized pictures, because they lead to this question, but we're also treating it mathematically in this picture. But then, as I said, have this criterion. So now one could somehow, I mean, it's actually turned out, this was a bit a disappointment for us, that it's extremely hard to evaluate this measure, even for very simple clocks. So if you give me a description of a clock, a theoretical description, for example, to quantum theory, then you should say, in principle, I should be able to now just be able to calculate what's the average time after which 2 copies of that clock fail to be ticking alternately. So we don't really have a solution for that. I think if someone finds a clever method to calculate that, even for simple cases, I think this would already be a very nice progress. So what we did instead is to somehow approximate that value. And an approximation, which is, I mean, in some way very good, but we don't fully understand how good it is, but intuitively it really captures exactly the same idea, is to say that let's just consider the average distance between 2 ticks. Now the distance, this is again, of course, relative, you could imagine, to external time, in the sense that you count how many boxes there are, but at the end we will again make it a dimensionless quantity. So it's only apparently depending on the background time. So let's say mu is the average distance between 2 ticks. And then you could also look at the standard deviation of the time between 2 ticks. Again, I'm now temporally referring to an external time. And now you could say that, I mean, of course, the standard deviation of a tick, if we again make this Markovian assumption, that which means that essentially things evolve independently of the history of how they evolve, then we know that the standard deviation behaves, grows like the square root of n. So the nth tick, the time when the nth tick happens, will have a variation that is of this size here, square root of n times the variation of the, if you want, the first tick. Now, of course, this alternate tick scheme, you get into trouble in the alternate tick scheme if the variation that you have of the nth tick is equally large as the distance between 2 ticks. That's essentially the idea. So to make this maybe a bit more precise, you could say that roughly the ticks are still alternating if n, this is the number of ticks you look at, is small enough so that the average deviation, the standard deviation of the nth tick is still smaller than the distance between ticks. And now if you just form this or manipulate this equation, you can say that this criterion fails if the number of ticks is larger than a boundary value, which I call R. And this boundary value is essentially just obtained by dividing this here by sigma and squaring. So that's a rough criterion to say when is the alternate ticks game lost, or how many ticks can you emit. And in the following, I will just work with this quantity, which has been considered actually in many works, in particular also by works of my co-authors, partially also with other people. And I will at the end give some references. Okay, so that's the measure. And now the question is, once we have such an operational measure, so you should still now operationally think of R as the number of ticks until you fail. So you can really think of this game, and there's a referee who just obtains the ticks from the two clocks and tells us when there was a mismatch. And so the question is now, what is actually this? What is the fundamental physical thing that bounds that? Could R be arbitrarily large? Probably not, because I hope I convinced you at the beginning of the talk that if you had only a qubit clock, only a two-level system, this is really not a good clock. I mean, how would you produce ticks from one qubit such that two such devices remain synchronized? It's probably intuitively already clear this cannot work. So the intuition should be that on the right-hand side, this bound on the maximum accuracy has to have something to do with the size of the clock. But now, in information theory, usually the size is not measured in terms of mass or energy or anything like that. And our arguments that we are trying to make currently and have made in the past in the group are really information-theoretic arguments. So we are aiming at a bound which is somehow really of information-theoretic nature. And this is maybe now where my talk starts to deviate from the standard literature, because in the standard literature, people usually consider, like for example, the accuracy of clocks depending on the energy that is available. So that's not what we do here. We try to find something which is of information-theoretic nature. And so what is that? What it turned out to be is something one could call the controllable dimension, or we called it like that. Maybe this term already exists somewhere because it's a very natural thing. So imagine that you have some device here. I just put a quantum computer, but it stands for some device that you somehow control well, a quantum device that you control well. Then you could ask yourself, what's the maximum correlation you can build up between this device, which I call S, and some hypothetical other system, just some memory system. And this correlation you measure in terms of the mutual information that is known in quantum information theory. So you somehow maximize the mutual information you can achieve between this memory and the device you want to consider you want to use as a clock. Now, of course, this can be large even if the left-hand thing is not a clock. But the point is, if the left-hand thing is used as a clock, this measure here will give us a bound. So this D control is, in other words, somehow the dimension of, you can think of it as the dimension somehow of the Hilbert space that you could use when you would do computations or something, if you want to relate this to quantum computation. So indeed, if you had a device that is good for computation, then it turns out that this controllable dimension would but just be the exponent of the number of qubits of the device. But in general, it's something more complicated, because this mutual information could also, I mean, you could also ask, for example, take a pendulum clock on the left. What's now the maximum correlation you can build up between a memory system and the position of the pendulum? And then, of course, the answer will at some point maybe involve stuff like energy and so on. So that will come out as a special case. But we are here on the abstract information theoretic level. We're just saying whatever this device is on the left-hand side, try to maximize the information content in that sense. So now I'm finally ready to state one of the main results we recently obtained in the group, and this is the bound. And it's actually a very nice formula. It strangely involves pi and the Euler constant. I don't know actually why this just comes up from the proof techniques, because it's a bound, so it's not clear that there is an equality. But it turns out that the accuracy, so the number of ticks that two clocks can emit in a synchronized manner, is always upper bounded by the square of the controllable dimension. So in other words, whatever you do in order to, or whatever you somehow however clever you are in designing a device, there is always a bound on the accuracy of that device as a time measure, as a timepiece, if you like. And this accuracy depends really on how much quantum control do you have about, or how much control do you have about the device. It turns out that this bound is also almost optimal. and this is one of the works I should definitely cite. I think it's a very important paper that was written in this area. This is in the group of Markus Huber and in Vienna. They introduced the concept of quasi-ideal clock. So that's just one particular clock model, which of course is also in this domain of theorists. So it's something you just make up, you design your Hamiltonian, don't care whether it's experimentally feasible, but at least in theories. So the statement essentially tells us there is a Hamiltonian and a system that we can describe in theory, which achieves this bound up to the prefactor, essentially. I mean, there are some additional conditions I should state about that. So this is an asymptotic bound. And so this, or at least this achievability is meant to be asymptotic. So it's not true that for any finity, but in the asymptotic limit, you get to this square behavior. Okay, so let's compare that. I mean, I'm now almost done, and I think time is almost up, but let's compare that to clocks we know. So I, at the beginning of my talk, showed you the Earth as a clock, and you could even imagine some bigger system. You could, instead of the rotation of the Earth, take as a system the rotation of the Earth around the Sun, instead of the rotation of the Earth around itself. So in that case, what you find is that the R value, so this is now not via the bound, this is just a direct calculation. How accurate is the Earth as a timepiece? And what you find is that the accuracy, in terms of this accuracy measure that we introduced, is of the order of n would be the number essentially of atoms of the Earth, if you like. So this determines how precisely we can somehow determine its position, the mass of the Sun around which it's rotating, and here the frequency of the rotation around the Sun. And the important thing is that it scales essentially linearly or squarely, if you like, with the size of the system. And this is also true for the modern way of measuring time. If you ask yourself, how accurately can atomic clocks, or how accurately are atomic clocks, then roughly this accuracy measure R, if you calculate it, scales with n, where n is the number of atoms you're using in this device. I mean, the atoms, or the cesium atoms, for example. And here you can make an improvement by using using certain quantum features of the system. But it's still at most square in the size of the system. And this really contrasts now to if you had a fully like a system like a quantum computer that you really fully control, in the sense that you could really design the Hamiltonian arbitrarily, in which case the scaling is exponential. So what this tells us is that if we really want to go much further with the precision of time measurements, we should in principle go to systems where we have full control of the Hamiltonian, so to speak. And if you have full control over a certain number of qubits, then we can hope to achieve clocks whose accuracy essentially scales exponentially in the number of qubits. Now I should remind you of the disclaimer I made at the beginning. And this is very important. I don't want to move that under the carpet. Of course, that's only the fundamental bound. So this is just telling you, once you have a perfect, let's say, n-qubit system with a perfectly controlled evolution, then the accuracy would be 2 to the n. But it's not telling you that there are no other difficulties. So of course, we still have noise and so on. But the hope is that, I mean, we also have learned in quantum computing how to actually deal with noise. We have fault-tolerant computing. So the hope could be that similar ideas, similar to fault-tolerant computing, could be used to actually build a device where we have a certain number of qubits, which are kind of logical qubits that we could use as a clock, which are really coming very close to this theoretical desire that I expressed before. Okay, I think this brings me already to the end of the talk. So I hope I could convince you that it's interesting to look at the problem of measuring time from an information-theoretic perspective. And I think still very little is known there. I think this whole domain has been studied a lot from like, of course, I mean, it's a very well-studied domain in general, clocks. Of course, people who devise atomic clocks and quantum clocks and so on, they have extremely good understanding of what makes accurate clocks. But if you look at the results, they're mostly not of this information theoretic nature that I presented here. And I think this information theoretic view could give us a new perspective on the problem and also give us new bounds, as I just demonstrated, a bound which is in terms of how much correlated can we be with a system. That's really an information theoretic bound. I show it here again. So the left-hand side is just the accuracy of the clock, but the right-hand side is really an information theoretic measure. And that's something that I think opens many interesting directions. And I will certainly in my group continue to work on questions like this. And we hope that we can, with that, get a better understanding of the fundamental limitations to time measurements. Okay, that's it. Thank you very much for the attention. I also put here some of the recent preprints we have. There are, of course, also many references within them, but I want to in particular thank my collaborators, Misha Woods, Ralf Silva, Gilles Pütz, Sandra Stupar. Oh, here is an error. This should be Sandra Stupar. I'm sorry for that. And Yuxiang Yang, who is, by the way, I mean, Misha Woods and Yuxiang Yang and Ralf Silva are still members of my research group. Yuxiang Yang is just about to leave for an assistant professorship in Hong Kong. So he may be a bit closer to you in Singapore. And I'm sure he would be interested also to continue in this research direction. Okay, thanks again for the attention.
Yeah, thank you very much for a very interesting talk. So please, if you have any questions, either ask them in chat if you don't want to ask them directly by unmuting your microphone. So one question I have is kind of, so this is one particular model, this ticks, and comparing how long they can kind of be stay synchronized. I mean, have you thought about other ways of quantifying the quality of clocks, and maybe yes, those are more
yes,
yes, have some problems, I guess.
Yes, so I mean, this is a very good question, and actually I think what took longest for me, if I look back in the development of this project, I think I spent almost 3 years without writing a single line, just thinking about what would be a reasonable way to quantify the accuracy of the clock without assuming already a background time. I think this makes it difficult. If you put that as a requirement, that you want to have something which is independent of already having somehow the Schrödinger time parameter in the background or so. And then I always came up to this same thing. And I was really thinking for a long time about other things, because one would just ask yourself, for what do you use a clock? And then you can say operationally, you should try to be able, or you should be able to quantify the usefulness of a clock without even knowing that there is, for example, a time parameter t, a Schrödinger parameter. I could just go somewhere and say, look, here are clocks. How would you quantify their usefulness without using something else? But if you cannot use anything else, it always has to do with somehow at the end the correlation of the clock. So I was at least not able to find anything else which satisfies the criterion of being independent of the background time. But of course, I would never try to claim that this is the only one. I'm just claiming I tried hard to find other things and didn't. And it would be extremely interesting to find other measures. Of course, there are many other measures, but other measures that satisfy the criterion that they are not already assuming an absolute time in the back, or a perfect time in the background with respect to which you measure it.
Yeah, or some kind of referee that has a clock that.
Right. Yes. Yes. And of course, in reality, it's also done a bit like that. I mean, if you ask yourself, how do you evaluate the best possible clocks? Of course, you have no other reference because it's just the best clock, so there's no better clock to compare it with. So what you do is you really run the clocks with respect to each other. So in some way, this measure is really in some way capturing what we can do and actually do in practice.
Yes. Okay. Yeah, I mean, I guess there is still room to explore somehow to find.
Yeah, definitely. Yes, I think
and
it would be really interesting to explore that further. Yes.
Maybe using more than 2 clocks. Yeah.
Yes, I think this would really be a nice topic also for information theorists who are, of course, very used to think about scenarios which not only consist of two-party correlation, but n-party correlation. And then you can ask yourself, what are other interesting constellations where, for example, in practice, you actually use clocks. I mean, my approach of thinking about this was always to go back to the question, what can I do if I have a clock? What does it allow me to do? And as I said before, having a single clock, whereas no one else has one, would be completely useless. That was my conclusion. And then if you have two, you start to have this use. But maybe if there are many more or interesting scenarios that maybe go beyond that, there could be a lot to explore in principle. Yes. So I think it's still a very open field to look at these things.
Okay, thanks. So there's one question by Mohammed Malik. Do you want to ask it yourself, or should I? Okay, so the question is how you rate entanglement purification for qubit computing for non-localized synchronization. I'm not sure I understand the question. Maybe you see it in the chat.
Yes, I see it. Okay, I'm not quite sure, but I think there is indeed something that is interesting, maybe also relating to your question, Mark, before. What can we do with more clocks? So one thing we are looking at is that if you have several clocks, if you have a network of clocks, can you somehow, and by combining now the information provided by the different clocks, have a de facto better clock? So you're somehow combining information coming from many clocks and are outputting a better clock signal. That's again something that is actually done in practice. I mean, there are many atomic clocks in the world, and there's somehow a scheme which weights the quality of the individual ones and then says this is the universal time, the world time. I guess this is done somehow like this. And now if you look at this from the more information-theoretic perspective, of course, this scheme that is used in practice works well, but it's almost certainly not an optimal one from an information-theoretic viewpoint. It's not the one that optimally extracts information from the available one from the clocks. So you could do something like a purification. I mean, if you now again have this picture in mind of the correlation between clocks that is somehow relevant. I think I briefly go back to that because I think this is maybe useful. Okay, okay, the one on the bottom here. Then you could ask yourself, okay, if you want to increase the accuracy of clocks, and imagine on the left-hand side you have many, on the right-hand side you have many, then you can do something which is similar to entanglement purification. So that's relating now to the question. So you could indeed apply ideas from entanglement purification to somehow purify the correlation between two sets of clocks and make it two, like you have, let's say, on each side n physical clocks, and then you could kind of distill from these n physical clock one on the left and one on the right, which are much stronger correlated than the original ones. So in that sense, that's very much like the entanglement distillation setting, and such things can be studied. We went a little bit in this direction. We have some work on kind of boosting the accuracy of clocks in that way, but I think this is again largely open. And again, I think it's very interesting to study this because no one has essentially studied the information theory of clocks. And that's a typical information-theoretic question, which is also practically relevant, by the way, because as I said, the world time is determined a bit in that way.
This is Mankei Zhang. Can I ask a question?
Yes, sure.
So I skimmed through your first paper by Woods et al.
Mm-hmm.
And there's also a bound in there. Is it different or is it similar to the bound that you just presented?
Yes, so thanks for bringing this up. So in the first paper that is on my reference list, so I didn't now state all results we have because I wanted to focus essentially on this fundamental bound on quantum clocks. Mm-hmm. Now I think the screen sharing stopped somehow. Let me start it again. Okay, I hope you can see here this slide. Do you see a slide now? Okay. Now let me go to the last one with the references. This is somewhere here. So in this, I think you mean this paper here.
Yes, exactly.
Well, this should be really Sandra Stupa. So in this paper, we actually had a result on what we called classical clocks. I didn't introduce this concept so far, but you could imagine like everything is defined as I did it today, but then you assume that there's so fast decoherence that the clock essentially acts like a classical probabilistic system. And then we also get a bound, and the bound there is basically the same as the one here, except for this squaring here. And the prefactors are also different. So what we actually showed there is that if you take the best classical probabilistic clock in that sense, so as I said, you have so much decoherence that there's no quantum coherence left, then this reduces the fundamental or the maximum accuracy you can achieve by a square root. That's compared to that result. However, because this result is tight in the quantum case, you can really then conclude from this that quantum clocks, that the coherence is really useful, that you have a reduction of a square root in the accuracy if you don't make use of the coherence of clocks. So okay. That's then essentially the other bound that is in that paper. And that was also actually very hard to prove. So of course I should probably should have mentioned it as well, because it was for us a big step to achieve that classical bound. But somehow I wanted to really focus on this aspect. We have now an understanding which is fundamental in the sense that according to our best possible theory, which is quantum theory, we get that maximum accuracy.
So I skimmed through that paper, and it's correct me if I'm wrong, but it seems that the physical origin of that bound is because of the measurement disturbance. Is that right? Is it because you are doing sequential measurements that
yes, you
have
could see
measurement?
It like that, yes. Mm-hmm.
But the thing is, in quantum metrology, we've been studying quantum back action noise for many decades.
Mm-hmm. Right.
And we know now that quantum back action noise is not fundamental. There are many ways of evading quantum back action noise. So I'm just wondering if you have made the connection between your work and quantum back action evasion.
Okay, so maybe I should say, okay, when I said it comes from quantum back action in the proof, I don't think we have this model that I mentioned before, which is this Markovian model that, okay, appears somewhere here. Yes, so we have at the end a Markovian model of this. And now, of course, in this Markovian model, what you call measurement disturbance and what is back action and so on doesn't really occur explicitly. You just assume it's an arbitrary map of this type, and then the bounds hold for this arbitrary map. Now, indeed, what would be interesting, and we haven't done that, is now to say, let's now look at specific maps that have been, that model clocks. For example, if you now say you have techniques to minimize the disturbance, that would also at the end be a map. And it would be interesting to see whether these are then maps which come close to this maximum bound that we achieve. And this we haven't done, but I would certainly be interested to do that. So that's, but you see the bound, we didn't really look at measurements explicitly in a sense. So there's not.
But do you assume any sort of specific interaction? Sorry.
Pardon?
Do you assume any specific interaction between the clock and this tick registers?
No, we look at this really from this information-theoretic level, where when we, for example, in information theory, talk about an arbitrary quantum operation, we are just saying it's some completely positive map. Of course, by saying that it's an arbitrary, completely positive map, we implicitly make a Markov assumption. That's why I mentioned the Markov assumption. But I don't think we make any other assumption apart from that one. So a completely positive map is just the most general thing that can happen if I assume that the correlation that comes in potentially from the environment is not correlated to the past. And that's the only assumption we are making for these proofs. So in that sense, my answer is no, we are not assuming a specific interaction.
I see. But of course, you can always go to the church, right? I mean, you have a CP map, but if you go to the church, then everything is unitary. So I'm just wondering,
yes, that's
what assumption you are making.
Yes. So actually, when we do that, I mean, it turns out, of course, that the usual problem that, I mean, we encounter a problem that is in some way well known in the whole literature on open quantum systems, that the Markovian assumption is only an approximation. Because if, of course, a real system always sometimes again gets influenced by stuff that it did before that went into environment and goes back. And if we go to this unitary picture that you're mentioning, then we would have to assume that the environment is, for example, arbitrarily big, so that nothing ever returns. So if you go to that picture, you get additional assumptions, but these are just the same assumptions that you would need to make in any other context where you assume a Markovian evolution of a system. So there's no additional assumption to that.
I see. Can I ask another question?
Yes, of course.
I
don't know, Mark has to say if there's no more time, but
so this R parameter, it reminds me of the signal to noise ratio or the mean square error. Mm-hmm. And you are relating it to some mutual information. So it reminds me of rate distortion theory. I'm just wondering if it has any relation to rate distortion theory.
Yes, I think this is a very interesting comment. And I'm not, I'm not aware of any, let's say, a relation one could, I would agree with you that it's related on this, let's say, I would say, level of ideas, but we couldn't make it kind of a quantitative relation so far.
I see. Of course, people have been studying quantum precision of clocks for many years.
Yes, of course, yes.
In terms of energy time uncertainty relation. So I'm just wondering if there's any relation between your bound and what people have been doing in terms of those things.
Mm-hmm. Yes, that's a difficult question, because this is all the time what we kind of course, here, that's also why I said in this talk, there's only, the new part is only really the last part with the bound, because indeed the other things have been studied to a very...
So perhaps the problem is not it's not as new as you claim to be. I mean, people have been studying this for a long time using quantum metrology, for example.
Yes, so. But that's exactly what I said. I mean, as I said, I didn't claim this is new.
Okay.
The only thing I claim was new is this bound here.
I see.
And yes, no, I'm just saying what is new is in some way the approach that we are taking, because if you look at, okay, I didn't now go into the kind of proof idea, so to speak, but I would say I have had some slides somewhere, I'm not sure I can immediately find them, but yeah, somehow the proof ideas, you can say you somehow really measure the correlation between two clocks in terms of information theory, in terms of mutual information. And then you can see how this mutual information evolves. And that I'm not aware of. So this kind of use of information-theoretic measures to analyze clocks and correlations between clocks is something that I'm not aware of. But if it exists, of course, I would be happy to look into it. And yes, I'm just not aware of anything.
The main measure, this R parameter, it looks really like the signal-to-noise ratio. I'm just wondering if. Anyway, so interesting.
Yes. So I think what is new is not. I mean, of course, the R, as I said, is just essentially a quotient between two well-known things, namely the yes. I mean, but the new thing is the, let's say, right-hand side. You see, there's this controllable dimension, which I would claim is really an information-theoretic measure, which is this. I mean, it's obviously an information-theoretic measure because it just involves mutual information. And the relation that this information-theoretic measure is related to R, that's essentially what we found. And to my knowledge, this wasn't known before.
No, this is very interesting, but it's just that in quantum metrology, people have been studying rate distortion theory.
Yes, of course, yes.
The use of quantum entropic
Yes.
information to bound mean square errors. So, so this is kind of familiar to me.
Yes, but okay, maybe I then misunderstood the question, because what I was saying, we are not aware that we can get this bound or something like that from rate distortion theory. So it seems to be something different. But this may also be the case. But our approach to derive the bound, I mean, we tried many things, and the thing that works is not really rate distortion theory. Of course, it's using ideas from there, and if you look into how it's done, then you may see many parallels to that.
I see. Interesting.
Okay, thanks. Maybe we should have.
I have a question.
Last question. Yeah.
From an experimentalist point of view, I have a question that is, if the two players, A and B, if the mu, I think, would be different, so the number of ticks in the background time would be different for the two players, then actually the two clocks would not measure at the same rate, correct?
Yes.
So that is what I would define as the accuracy of the clock, that actually the two clocks follow the same mu, the same kind of number of ticks that need to evolve in the background time before one full tick of one of the clocks A or B can actually emerge. Now you have that Markovian process, and if you idealize, let's say, your player A as an ideal clock without fluctuations, then that would take the role of the background time, right? And then you would reference the player B against that background time. And if clocks or tick failures in the tick comparison happen, this would not be really so much the accuracy from an experimentalist point of view. For me, that would be phase noise, actually. Could you comment on that?
Yes, so yes, maybe one should distinguish between the definition of the accuracy measure, which is, I mean, the definition of the accuracy measure are now without the mu and sigma. That's why I made this relation. So let's maybe briefly go to that one. Okay, I think this was before. Yeah, I don't immediately. Anyway, so let me just say it in words. So the accuracy measure that is defined in terms of the alternate tick scale, this was defined independently of the mu's and sigma. This is really purely operational. You take your two clocks, you don't really care about Markovian assumptions and so on. You just measure, look how well do they stay synchronized. And I would claim if you have only clocks, that's the only thing you can do. Now, of course, as I said, we couldn't, now in theory, that's now a theory problem. Now we want to evaluate this measure and see how does it behave depending on properties of the quantum system, on information-theoretic quantities and so on. And in order to evaluate it, or we found that it's extremely hard to evaluate it in general without making further assumptions. So we now move to this, we introduced these Markovian assumptions and then only talked about the mu and sigma. But if you ask me what is really a sensible measure, then I would say it's the one we defined before, the alternate ticks measure, the number of alternate ticks. And then the other thing is just for us a help in theory to analyze things and to make statements. So that I would consider much less fundamental. And indeed, as you correctly say, that because of the Markovian assumption, if you have, for example, also bursts or phase shift errors, that's not accounted for that. But that would be accounted still by the original measure. So in some way, we have this part where we say, okay, that should be the measure, the operational one, that's fine, they can always use it. And then we say, let's now analyze it for certain systems under the assumption that we have essentially perfect systems. This is now the theorist viewpoint. And here I'm moving away from experiments and saying, now let's analyze them. And if you are only interested in fundamental bounds, then of course we can say whatever gives us a bound is okay. Of course, in experiments, you have additional things, you have shifts and so on. And that's just not taken into account by the I mean, the bound is already there without that. It's a bit like Heisenberg's uncertainty principle. That bound is there independently of whether you have other sources that disturbs your measurement. And so in that, maybe the summary of my answer is I agree that in reality, I would agree with your statements. Just make the point that there are kind of two measures that I introduced. The one, the really fully operational one, and the one which is this quotient between mu and sigma, which is much more constrained to one particular type of error.
Thank you.
Okay. So let's see. So I think we are already a lot over time. So if nobody has a very urgent question, then maybe we should wrap this up. Yeah, thank you very much again for this.
Thank you again. Thanks everyone for listening and for the good questions. And indeed, if anyone has any input or something, let's say some ideas on the points where I mentioned that are open, also literature that I should have cited or not, please send it to me. It's always a bit the risk to talk about. I mean, in quantum information, you are in one field and then you are branching out to other areas. And then, of course, it's very easy to miss things. And I'll, of course, be very happy to take into account everything, even if it turns out that this result that I presented was somehow already known in another branch that I wasn't aware of. Okay, but thanks again. And it was nice to see you and also many others. And I just saw Valerio was quickly turning on his camera. Hi Valerio.
Okay, then yeah, thanks a lot. And I hope to see you sometime here in person.
Yes, or you come here.
Well, yeah, that will probably
the other option.
happen soon.
Yeah.
That will
But at the moment, it's difficult, I think.